In this video, we're going to be covering Objective 3.4, the ideal gas law. Our topic is to explain the relationship between the macroscopic properties of a sample of gas or mixture of gases using the ideal gas law, and our skill is mathematical routines. This is our second video on Objective 3.4. The key point of this video is that in a sample containing a mixture of ideal gases, the pressure exerted by each component, the partial pressure, we call this the partial pressure, that's the pressure exerted by one gas in a mixture of gases, is independent of the other components. Therefore, the total pressure of the sample is the sum of the partial pressures. So this is written down here, where the partial pressure of gas A is equal to the total pressure times the mole fraction. So this is the moles of A over the total moles. So let's say only 10% of the moles, 0.1 were moles of A, and the pressure was 10 atm, then we would do 10 atm times 0.1 to get the partial pressure of just A. So that's the pressure exerted just by gas A. And to find the total pressure, we're doing all of the partial pressures added together, depending on how many gases we have. So this could be 10 different gases. This could just be 2 different gases. So we call this Dalton's law of partial pressure. And just to really show you visually how this works, if we have this heavier particle, this blue particle, and I'm going to just hold the volume constant, not change that size, and we add, so now we've added 50 heavy particles. Notice the pressure is around 6 atm, 5.5, 6.1, it's around there. So let's say we take another gas, even though this one's lighter, we're going to add 50 of those. So now we have 50 heavy particles and 50 light particles, and the pressure has just about doubled. It has doubled. And so our total pressure, our PT, is the pressure of our heavy plus the pressure of our light. So it's the pressure of each of these different gases. And since it's 50% heavy and 50% light, the mole fraction of the heavy and the light is there's 0.5 heavy and 0.5 light. So if we multiply this pressure by 0.5, we would get the partial pressure of our heavy gas. And if we multiply the pressure again by 0.5, we would get the partial pressure of our light gas. Notice it's about 6 for each. Which is what we did when we just had heavy. You could see that it exerts a pressure of 6. So if we had more light, so now we have twice as many light particles as heavy particles. So we have a total of 150 particles. So our mole fraction of heavy would be 50 divided by 150, or 0.333. So then if we multiply our pressure, like 17.5 times 0.333, we'll get about 6, a little less than 6 atm, which is what we had initially. And then for the light, to find the partial pressure, we would do 100 divided by 150. So that's 0.666 with a repetend, or 0.67, times our total pressure to find the partial pressure of our light particles. So our first practice, when 4 liters of helium gas, 6 liters of nitrogen gas, and 10 liters of argon gas, all at 0 degrees Celsius and 1 atm, are pumped into an evacuated 8-liter rigid container, the final pressure in the container at 0 degrees Celsius is... Okay, so we have a lot of information here. We know that helium, we have 4 liters of helium, and it's at 1 atm because everything's at 1 atm. The temperature is not changing, so we don't need to worry about that. We're really focusing on volume and pressure. We know that we have 6 liters of nitrogen. I wrote neon, I apologize, that's nitrogen, and at 1 atm. And then we have 10 liters of argon at 1 atm. So if the container was 20 liters, if we added all these together, it would have a pressure of 1 atm, because the helium would be 4 out of that 20. So let's say, to put this another way, let's say to get this pressure, we have 4 moles of helium. We have the same pressure for nitrogen, the same pressure, it's 1 atm, but we've increased the volume. So that means we've increased the moles. So we would have 6 moles of nitrogen. And we would have 10 moles of argon because, again, we've increased the volume, but we've kept the pressure the same and the temperature is constant. So according to our ideal gas law, PV equals nRT. If we've increased the volume and the pressure is constant, our gas law is constant, it's always constant, and our temperature is constant at 0 degrees Celsius, we have to increase the amount of moles proportionally. So if our volume is 4, that would mean we can assume we have 4 moles. And it's just really about the proportions of these. It doesn't really matter the exact number. And so this would mean we have a total of 20 moles. So if the container was 20 liters, it would have a pressure of 1 atm. But the container is not 20 liters. It is 8 liters. So we know that the pressure is going to be higher than 1 because we've decreased that volume. So that means we're increasing the pressure. And we can use this equation, P1 times V1 equals P2 times V2. So we know that if the container was 20 liters, so if our volume was 20, then we would have 1 atm. Our pressure would be 1 atm. But we know that the volume is actually 8. So then what is our final pressure? And so our final pressure would be 2.5 atm. A gas mixture at 0 degrees Celsius and 1 atm contains 0.01 moles of hydrogen gas, 0.015 moles of oxygen gas, 0.025 moles of nitrogen gas. Assuming ideal behavior, what is the partial pressure of hydrogen gas in the mixture? So we're looking for the partial pressure of hydrogen. So we know that the partial pressure of hydrogen is going to equal the mole fraction of hydrogen times the total pressure. Remember, the mole fraction of hydrogen is the moles of hydrogen divided by the total moles in this whole mixture. So our total moles, we're just adding these up. We have that many moles of hydrogen, that many moles of oxygen, and that many moles of nitrogen. So therefore, we have 0.05 total moles. Okay, so that's our total. And we know our moles of hydrogen, so then we can find our partial pressure, our mole fraction of hydrogen. So we're doing the 0.01 divided by 0.05. So that's the same thing as 1/5, because if I multiply the top and bottom by 100, I would get 1/5. So you should be able to do that math in your head, where our mole fraction would be 0.2. And then we're just multiplying that by our total. So our total pressure, we're told, is 1 atm. And so the partial pressure of hydrogen is 1 atm times 0.2 atm. And this is because H2 is 20% of the total number of moles. So 20% of this gas is hydrogen, therefore 20% of the pressure is the partial pressure of hydrogen. Equal masses of 3 different ideal gases, X, Y, and Z, are mixed in a sealed, rigid container. If the temperature of the system remains constant, which of the following statements about the partial pressure of gas X is correct? So we're told we have equal masses, we have 3 different gases, and we have a rigid container. So we're not changing the volume of the container. The temperature remains constant as well. So we know that the partial pressure of X is equal to the total pressure of X times the mole fraction of X. So remember, the mole fraction is the moles of X divided by the total moles. We don't know the moles, though. We just know the grams. So A can't be right, or it might be right if these were all the same gas or had the same molar mass, because then we would have the same amount of moles, but we don't know. For B, it depends on the intermolecular forces of attraction between these molecules. We have an ideal gas, so we're assuming that there's no intermolecular forces. It depends on the relative molecular masses of X, Y, and Z. Yes, we need to know the molar masses in order to get our amount of moles. And in order to find the partial pressure of X, we must know our amount of moles. It depends on the average distance traveled between molecular collisions. That doesn't really have anything to do with this. And it can be calculated with knowledge only of the volume of the container. It's a rigid container. The volume's not changing. And in order to know the partial pressure, we just need to know the mole ratio, the moles of X. So therefore, C is correct. Diagram 1 shows equal molar samples of two gases inside a container fitted with a removable barrier placed so that each gas occupies the same volume. The barrier is carefully removed as the temperature is held constant. Diagram 2 above or below shows the gases soon after the barrier is removed. Which statement describes the change in the initial pressure of each gas and the final partial pressure of each gas in the mixture, and also indicates the final total pressure? Okay, so notice we have the same amount of gases. It says equal molar samples of two gases at the same volume. So let's say that our pressure of this one was 1 atm, and our pressure of this one is also 1 atm. Well, when we've removed this barrier, we have doubled the volume. So if we ignore all the white particles in this final volume, the pressure of the gray particles is 1/2 atm, because we have increased the volume. Sorry about that too, that's 1/2. We've increased the volume, we've doubled the volume, but we haven't changed the amount of particles. So since the same amount of particles have twice as much volume, the pressure has been halved, it's 1/2. And so the pressure of our white ones are also 1/2 atm because of the same reason. We have doubled the volume without changing the temperature or the amount of gas. And so our partial pressure of both of our gases has been cut in half because we've doubled the volume. However, the pressure of our final mixture, we need to find the pressure of our final mixture, we need to add the partial pressure. So we're really doing 1/2 plus 1/2. So the total pressure in this substance, in this mixture, would be 1 atm. So it would be the same pressure, and this, we could call this X atm because we don't know that it's at 1 atm. So this is X atm, this is X atm. So now we have, we've cut the X in half, right? We've cut that pressure in half, so you could have 1/2 X atm as our partial pressures. So then we would again have X atm as our final pressure. And so the partial pressures of each gas in the mixture is half the initial pressure because we've doubled that volume, but the final total pressure is the same as the sum of the, oops, not that one, sorry. That would mean that it would be 2x. So it's going to be this one. The partial pressures of each gas in the mixture is half its initial pressure, right? We've cut that in half because we've increased the volume. And the final total pressure is half the sum of the initial pressures of the two gases. If we do X plus X, we get 2X, but really our final pressure is just X. The final pressure, because we've doubled the gas and we've doubled the volume, the final pressure will be the same as the pressures that were initially. Okay, try and complete this one on your own, and we'll talk about this one during class.